Okay. So far we have been covering these operations. We had to do search, we are doing insertion, we are doing deletion, and we are doing traversing, right? Right. And search, insertion, deletion, traversing. Linked list search takes order of n. Insertion takes order of 1. Deletion takes order of 1, order of constant. And traversing is order of n. In the binary search tree case, because that we have the we are limiting the search directions, search passes, the order of the binary search tree reduces to the log operations. And why is that? Why is that? Why this is reduced to the log operations? Because that in a nice world, if imagine that binary search tree is what? In the binary search tree, let's imagine it's a full tree. In the full tree case, this was what? Log of the s, right? Logs, and it followed this formula, right? In the up here, sorry about this whole thing, but I'd like to show you one particular characteristic that we already found out in the previous note, right? Here it says log d and s, and these are all some kind of additional coefficients. So what it really matters here is log d and s. And we have that log, right? In the full tree assumptions, this height is log d and s with some constant, right? And this s is actually the n, right? Size is actually the n number of nodes, right? N number of numbers to find out. So log dn, and here is log 2n. Log 2n is the maximum height. Means that in the full tree assumptions, it can be log 2n operations. It can be log 2n operations. The search can be. It's enabled because that we don't have to search through this area. We don't have to search through this area. We only have to search through this area. So that's how we achieve this log n efficiency. So binary search tree in average full tree like structure, it looks like this. And insertion is order of constant, deletion is order of constant, and traversing is still order of n. If you go back to the previous slide sets, you will find out this. However, there is an important assumption of this efficiency notation. Binary search tree in average case, binary search tree in the full tree like structure is the log of n. However, binary search tree in the worst case, this is perfectly okay binary search tree. This is valid binary search tree, but it doesn't utilize any left-hand side. It doesn't utilize any left-hand side, means that it's the same to this what? Linked list. It's only using the right-hand side as a reference get next method, and it means that it's nothing better than the linked list. In this case, this height can be n, and it's going to be order of n searches, and these are all the same. So binary search tree, by by looking at this shape, efficiency differs a lot. And we want to keep that this way. If we want to keep the efficiency in this way, and we don't want to see this efficiency. However, in the worst case of this binary search tree, still it works like the linked list. So that's the problem. And that's the problem that you want to tackle in the next week, right? So the readings is this, and it's a good book. Please go home and read, and then please write down whole this program and see how it works, all right? So that's the thing that I have, okay? So there is one mistake, and it's not, this is right, okay? So have a good time, and I will see you in the next part of the week, week video, right?